Good afternoon and welcome to our Red Train session this afternoon. I'm delighted to see so many people in the audience here in the studio, and welcome to you who are joining us online. Today our guest speaker, our research giant, comes from the Center for Composite Materials and Structures at the Harbin Institute of Technology in China. Professor Jinsong Leng has a fantastic record. He has authored more than 290 scientific papers, 110 books and book chapters, 37 patents he's responsible for, and he's delivered more than 80 invited presentations around the world. He's going to talk to us today about smart composite materials and structures for next generation applications. So without further ado, I'd like to welcome Professor Jinsong Leng. Thank you. Nice to see you.
Nice to see you.
Here's a little commemoration.
All right, thank you.
As you've been recognized formally as a research giant here at USQ.
Thank you.
Over to you.
All right. Good afternoon, everybody. First of all, I thank Peter for a nice introduction to me. This is my third time in Toowoomba to visit the University of South Queensland. So I'm very glad to get this award and give a talk about the smart composite materials and structures for the next generation applications. So I come from the Center for Composite Materials and Structures, which in Harbin Institute of Technology. Right. So before I start my presentation, I will little bit introduce the city of Harbin in China. So you can see China's here, and actually Harbin is located in northeast of China, which is somewhere here. If you're coming from the capital of China, from Beijing, it takes about 1.5 hours by airplane to reach Harbin. It's nowhere far. Harbin actually is famous with ice sculptures, and also is very good in summertime. So our university is called Harbin Institute of Technology. So we have 3 main campuses along China, in Harbin, in Weihai, which is coastal city nearby South Korea, and also another campus in Shenzhen, which just cross border to Hong Kong. So in the main campus, so we have a faculty member about 2,900, and also the total student, full-time student, is about 50,000, including the undergraduate student, postgraduate, and overseas student, which are around 2,000. So we have 23 schools in the main campus, Harbin, and the research funding is about $300 million for the last few years. So we belong to School of Astronautics, which we have more than 300 faculties, including 140 professors and associate professors, which is another 100. And also we have around 3,000 students, including undergraduate and postgraduate students. So now I can start my talk for smart composite. So what is smart materials? So talking about smart materials, you will see, I don't know how this one is working, right? Okay. So you will see the smart materials will have some sensor materials, will have actuator materials, and host materials, and the control system. So with this one, when the environment changing, the sensor materials, which is sensor, can sensing the environment changing, then send the signal back to the central system, then send a control signal to actuators, which can control the shape changing to the adaptive and also do the self-healing in the futures. So for my talk today, I will target the new smart polymer, which is a shape memory polymer, and also some applications in the deployable space structures and the morphing structures, and also other applications. And the last one, I will talk about some other research activity in our research group in HIT. So we start with the background. So what is the shape memory polymer? So shape memory polymer is one kind of shape memory materials, which based on polymer. So this one, the phenomenon is similar with another shape memory materials, which is shape memory alloy. So the initial shape for the shape memory polymer, like this one. So, and if you heating above 2 Tg, the material becomes very soft, which means you can apply some load to changing the materials to different shape as you want. Then if you cooling down below 2 Tg, the material can keep the shape, means energy can be stored. Then if you heating again above 2 Tg, so the material can recover to original shape. So all of this phenomenon similar with shape memory alloy. But different thing is, remember, that's polymer-based shape memory materials. So this is another few things I want to show you. A means this is a pure polymer and here, and also you can reinforce with some composite, even glass fiber or carbon fiber and whatever. So with this one, the polymer can changing the shape upon the stimulus you applied. The stimulus can be heating source, magnetic field, water, sunshine, whatever you like. So this is a comparison with the shape memory polymer and the shape memory alloy. So the polymer, which is called SMP, have some advantage, like long density, large deformation, and also the required stress for deformation is only 123 megapascal, compared with another shape memory materials, which SMA, normally you need 50 to 200 megapascal. And also the transition temperature is wide, and also processing condition easy. And very important is the cost is lower than SMA. But this one also have some drawback. One is the recovery speed. Another one is the stress generated upon the recovery is lower than SMA. So the advantage I mentioned for the SMP have some low density and also biodegradable and low cost. But main challenge is how to driving. So you have SMP, you can heating above 2 Tg using heating gun or using water. But for the re-applications, you need to do something. So the solution is you can make some composite. To make a composite, so you can have a new actuation method, and also you can improve the mechanical and the recovery speed and the mechanical property as well. So you can see SMP plus filler, and you can get a composite. So this map to show you the comparison of the different typical materials. You can see they have a SMP, have a PVDF, nylon, and CFRP, and also have some soft materials, which like PN elastomer form. But only SMP have two potential here, which I plus here. One is the hard. This is said hard. That means below 2 Tg, the materials is very hard. Have few gigapascal with Young's modulus, but a few percent with elastic strain. But if you're heating above 2 Tg, the material become to very soft, like elastomer, which have a few 100% of the elongation, but the modulus is only a few pascal. So we also call SSMP is special smart materials, which stiffness can be changed upon the stimulus. So this one kind of stimulus wearable materials. So right now around the world, I have lots of people working in this area. I think from Web of Science, you can see about 3,000 papers published. So they have a few major research groups around the world. From Air Force Research Lab USA, they target working with the thermal setting shape memory polymer and also some composite structures. From Germany, by Dr. Andres Landry, his school working with biomedical for the biomedical applications. From Hong Kong, Professor Hu, he working with smart textile. And from Syracuse, Professor Patrick, Syracuse University, he also working with biomedical applications. So we are working with something smart composite and actuation method. So some typical applications, you can see like a wind turbine blade. So I cannot point where I'm talking about. So for the wind turbine blade, traditionally, wind turbine blade the shape cannot changing. But if you're using shape memory, composite polymer, the wind turbine blade can changing shape upon the stimulus. So this one will give you better energy generation efficiency. And the right-hand side is from LC Dover, US company. They made called mid-expandable habitat. It's for the move. You can see this one deploy if you apply some heating source. And they also have something called switchable information carrier, which means the pattern can switch upon the stimulus. You can give you a different pattern, upon the stimulus. And also, this has a self-healing capsule. So with this one, the capsule can be deployed and the drug can release easily. And also for optics, the things can do with micro optics. If you have some micro grating, the grating shape changing and the optical property can be changed. So they also can do another things. In the right-hand side is called smart textile. You can see the code, the shape, the fabric, woven by stream memory polymer. This can changing shape. And also there's somebody working from US, Dr. Jerry Chi, working with 4-dimension printing to printing different kind of smart structures. So this is another way using stream memory polymer combined with stream memory alloy. So with this one, you can do two-way actuations. One by SMP, stream memory polymer, another by SMA. So the bottom one is another of my colleague who using the photoresponsive flexible graphene oxide polymer composite. With this one, it looks like equilibrium apparatus. So with the light, you can see from the movie, this one is changing. It's driving by the light. So for the polymer, you have pure polymer, so you can do a lot of things. You have polymer matrix, you can make a fiber, you can make a membrane, you can make a foam, also you can make a composite. So the matrix. So in HIT, in our group, we start making some thermoplastic and thermosetting stream memory polymer. With different transition temperature, we start using the polystyrene, which transition temperature around 70. Then we go into epoxy, standard ester, which is around 250 degrees for the TG. And now we develop a polyimide, which is go to the higher transition temperature for SMP, 320. We also produce some thermoplastic stream memory polymer, which used in potential for the biomedical applications. So I take some initial published paper to show you what we have done during the last few years. This is a standard ester based high transition temperature SMP. So the range is around 250. And also we can see the recovery ratio is 98%. So we also produce some polyimide. So with the polyimide, you can see the transition temperature is around 320. So this one is also good with the UV resistance. So you can see this one with just 10 seconds, you can see the sample can deploy. And also recently, we published a paper in Soft Matter for the optic transparent high transition temperature. With this one is optic transparent. You can see this one, and also I want to play the movie for you. I'm not sure if that one working. Maybe I need to come back. No? Okay, I'll show you later, because this one is very used for the future mobile phone. Because in the future, we have something like a transparent and a flexible mobile phone. The polyimide is very good substrate to make that. So if we can have a flexible stream memory polyimide, we can make a lot of optical devices, especially for the flexible optic devices, like a mobile phone or something. So we also made some polyimide, BMI, which is also have a triple stream memory behavior. That means normally ship memory polymer have just from 0 to 1, which is just one transition temperature. But with this one, you have 2. That means this polymer can remember 2 or 3 shape. So we call it triple. And we also can make with some membrane, ship membrane polymer fiber as well. So it takes some example. So this is we made by Norfin. This is also multi-shape ship membrane polymer membrane. You can see from 160 degree, 135, 110, they have a different shape, which means this one can remember for 3 different shapes. So we made some also biocompatible ship membrane polymer, which we call the chitosan, and also to make a membrane for the scaffold for applications. And also this one we made the cold shell ship membrane polymer fiber. Initial idea is we have the ship membrane polymer which made by epoxy. It's a ship memory, but this one is not biocompatible. So we make a cold shell with PCR together. So with this one, you can have a biodegradable property, biocompatible property, and also this have very fast ship recovery time. And also we can make some foam. You see the foam made by PCR, and the initial temporary shape is has 1 centimeter and 3 centimeters, and you can have a temporary shape 1 centimeter. Then you're heating by microwave or by water, this shape can change. So we also can make another one, which is polyurethane foam. With this polyurethane foam, the compression ratio can up to 90%. So then we can make a composite. So to make a composite, we can using a lot of different filler. We can either using some nickel powder, carbon black, carbon nanotube, carbon nanofiber, or we can use some graphene and reduce graphene oxide paper for the electrical actuation during the dual heating. And we also can do some the water actuations or the magnet actuations by using some iron oxide and also light actuations and the microwave as well. So this is, we start with the nickel. So why are we using nickel? Because nickel is the material sensitive both magnetic field and the electric field. So this graph to show you no magnetic field, nickel will distribute homogeneously in the polymers. If you apply magnetic field, nickel can form a chain. So what the idea is, we're using this one during the Q, during the fabrication, we're using magnetic field to form a chain. Then after that, after Q, the chain still survived. You can see from the ICM that after a few cycle bending, the nickel chain still survived. Then you can simply apply some voltage to deploy this one. So another idea is we using carbon black. So to using carbon black, this one also can improve the conductivities. So the ABC means different column. A means only carbon black, and B means have carbon black, but have nickel. But at that time, nickel is random distributed. And the C means we have carbon black. We also have nickel, but the nickel is a chain. So this one, you can see the color is bright and it's up near the 80 degrees Celsius, which show the better recovery properties. So we try a lot of different conductive particle. I don't want to say everything, but we try. This one is a short carbon fiber with carbon black. You can see the volume resistivity down to 2 ohm centimeters, which is just 7% of the filler content. And also we try using carbon nanotube. So the idea is we using AC voltage to align nanotube in the polymers. So you can see zoom from here to here, you can see the nanotube can form a chain. So after the chain formed inside the polymer by AC voltage, so you can simply apply voltage. During heating, you can heating the polymer to deploy. So for existing work, normally you need to distribute the particle inside the polymer homogeneous. But the problem is you cannot have too many particles. They will reduce the other mechanical properties. So the idea is we propose using another conductive element, which is called a bucket paper. The bucket paper is made purely by nanotube. It's very good conductivity, so we can laminate. This one is a composite. Using the bucket paper is a heating and a conductive element. So we done some work in this area. So we coated SMP with bucket paper, and we see this one can deploy from 0 second to 140 seconds. And also for the nanofiber bucket paper and the nanotube bucket paper as well. So we also grew some nanotube just between the bucket paper and the composite SMP. The reason is the SMP and the bucket paper have different thermal conductivity. So we grew nanotube just in between. And this one will improve the conductivity. So you can see the induction time is reduced. So we also try different conductive particle, like carbon nanofiber plus boron nitride. The reason we're using boron nitride is this one is very good thermal conductivity. With this one, you can see the sample can deploy from 0 second to 80 seconds very easily. So this is another one we want to do the multifunctionalizations. So because for the composite, it's conductive, so you can simply measure the resistance change if you apply some temperature or some other stimulus. So this is a sensor, and also this one can changing shape if you apply some stimulus. So you can see this is a mobile phone in the futures. The mobile phone will be flexible and wrapped to your arm. So if we have the shape memory polymer is a substrate, in the future we can deploy this one easily. So another one is we tried using PAN. With PAN is another conductive nanofiber membrane. With this one, we also can do the shape recovery during the zero heating. It's very fast, only 5 seconds. This one can deploy. So we also try another conductive paper, which is a reduced graphene oxide paper. For this one, it's all very fast. The graphene is very good conductivity. You can see the temperature distribution, and this, apply some voltage, this can deploy very easily. And recently, we using the carbon fiber field. This one is also is a heating element, also the surf sensing element. You can see the curve, this one, and also the temperature distributions. So the polymer also can driving by the stimulus, different solutions. So we found this phenomenon very early with some colleague in Singapore. So you see this physical swelling effect from 0 minutes to 60 minutes. The polymer can deploy very easy, but not only shape changing, it only changes dimensions, which means this one in the future, if you have drug inside the tube, can do some drug delivery. And for the thermosetting polymer, we do find epoxy also can driving by waters. You can see from the right-hand side, if you put the wire, which is red color in the polymer, this can deploy with 180 minutes. This because the polymer surface, we can have some SDS to make some hole to allow the polymer have more absorption for the water. So this is another idea using magnetic field. So using magnetic field, because we're using the iron oxide, this easy to absorb magnetic field, so this can change in shape. You can see the polymer shape changing from A to D, the shape can deploy, and the shape can change. So another design, you can design by mechanics to different consider magnetic particles, particle volume and the particle size to give you different driving performance for the magnetic field driving stream memory. And this is another one we want using infrared laser. So we embedded the optic fiber inside a wire. So you can see if you apply some infrared light, the wire can deploy. And this one in the future, if you have some like a thrombus in your human blood vessel, and this can change in shape, and after that you can remove your thrombus easily. So we also have collaboration with Leng, and we're using the nano zinc oxide nano particles to improve the UV. Because zinc oxide have good properties to resist UV light. So with this one, we can find with the nanoparticles the no degrades for the after UV degradations for the composite. So that means you can try a lot of composite to give you different properties for the shape memory composite. So we also try microwave. With microwave, you can see actually it's, because the carbon nanotube can absorb microwave. So with this one, you can have a fast actuation, and also the important is wireless and the distant control to control the shape changing. So this is a multi-stimulus responsive polymer, which means the polymer have some iron oxide and a contact particle. You can see this one can respond by magnetic field, then changing by electric field, then changing by the hot water, which is temperature. So changing different shape. So this one I want to emphasize is the recently published paper we called selective stimulus, multi-stimulus, which we using different stimulus, magnetic field, RF field, radio frequency, and the heating. So you can see the movie this deploy, but only this one part deploy upon the magnetic field. Other part is no moving. But if you apply the RF heating, so the middle part can moving. And if you put in hot water, but other part will moving. But this three part can be controlled individually. That means you can selective this one. We also make some self-healing composite with shape memory property together. So for shape memory, you can see from bottle, the graph, they can picture the shape can recover, but not only shape recover. We put some thermoplastic polymer inside, which can healing some crack. You can see the crack there, and afterward, the crack can disappear. So the surf healing efficiency is about 70%. So that means the polymer not only can recover on the shape, also can healing some crack. So now I'm going to talk about some applications. So for the first application is deployable. Traditionally, you can see this big antenna, 9 meter in diameter. It's very big. But traditional antenna using the mechanical devices and also some, complex structures. And also to deploy, normally using explosive bolt, which is not very steady and have dynamic impact to the satellite body. For SMP, you can easily think about it. It's easy to design and just shape changing upon the stimulus, which is normally temperature or magnetic field. So, but before to do that, we'll target very harsh space environment. They have vacuum, you have radiation, atom oxygen, and also the temperature variations. Here is the satellite, and this is the deployable antenna and also deployable hinge, which normally using explosive bolt. For the low Earth orbit, normally the temperature is from -100 to 100. For the high Earth orbit, normally we talk about -170 to 170 degrees Celsius. So that's why we develop different polymer to adapt different temperature range. For epoxy, the temperature range can up to 150. So that one can use for the low Earth orbit, which low Earth orbit normally -100 to -100, but our epoxy is out of the range. But that epoxy cannot using for the high Earth orbit, because high Earth orbit, the temperature is from -170 to 170. That's why we develop another higher TG, which is Center Easter, up to 250. So this is some published work for the epoxy-based polymer after gamma radiations. So we can prove after different doses of the gamma radiations and the temperature cycle, the polymer, how about the recovery ratio, the mechanical property, how about the shape fixity, how about that one? So we prove that one is still okay after radiation at the temperature cycle. That means this one can use in the space for the future applications. So we also done some theoretically work for the SMP and its composite. That means concept model. We start with the model of the shape memory polymer, and also the mechanism of the shape memory effect, and also the composite. So we do stress analysis and also the post-buckling. So I don't want to go to details, but I want to show you some model. This is the contour model for the shape memory polymer. Also, we try to simulate the multi-shape memory effect by using the standard linear solid model, which is there. You can see this one, we can simulate the triple shape memory effect. And this one is a composite, so thermal mechanical concept model for composite the shape memory. So you see the glass phase and the rubber phase. So I don't want to go to details, but this one is post-buckling, because for composite, it's very important for the buckling. You can see the single fiber, you can see the polymer after buckling. So what we have to do is we have to predict the wavelength and the amplitude of the buckling. So then we do some prototype design. So this is a prototype design for shape memory polymer hinge. So from this one, you see the hinge is initially folding and then deploy after maybe 800 seconds, which you can control. And this one, if you have the hinge, you can control the solar cell panel deploy, just by heating. We also made some truss. You can see the truss also made by composite plate. It's folding together. Then after, you can see from bottom one, from 0 second to 80 seconds, the truss can deploy if you just simply apply the heating source. So we also made some release devices. The release devices, the basic principle is like two parts, like my finger for holding together. If you want to release, you simply change shape, change this shape, then this can release. And also this can come back to is a lock. So we design different one. And the bottom one is called the lotus. So 7 small part holding with the bottle together, and this one can release. And above this, we call the twist one. You can twist this one inside the screw. Then when you're heating, this one can come to orange shape, which is left-hand side one, and take off. So then we're going to talk about some application in morphing. So this one is a morphing aircraft by NASA. They want to have this concept by 2030. So in the future, the aircraft hopefully can like that, can changing shape if you want. And can I play another movie, please? Nobody here? Okay, it's coming. So you can see this is by Lockheed Martin. They want to have this UAV can fold a wing, and then after mission, then they deploy again to come back to the normal status. So, but the target is for this one is very important, is the morphing skin. So right now have in the bottom, the top one, the next gen company, they're working with flexible skin using rubber. But the problem is for the morphing, you need shape changing. But you need shape changing, you need low stiffness. But low stiffness means you can change your shape but cannot stand aerodynamic load. The high stiffness, you can stand aerodynamic load but cannot change your shape. So that's why we need stiffness variable materials. So if you want shape changing, become to low stiffness. If you want to stand higher aerodynamic load, you need high stiffness. So right now for morphing skin, there are at least some three of here. One is called the fish scale structures, which is like a fish scale, but this one is not smooth. Another one is rubber materials, which you can reinforce with some reinforcement filler, but that's a low stiffness. Another one is corrugated structures. This, but the thing is it's only changing in one directions. So what we propose to do is we using shape memory polymer. Remember this one in the very beginning, SMP can change in stiffness from very hard to very soft upon the stimulus. Then you come back. So we not using SMP to driving the morphing structures. That's too heavy. But we're using this one to change the stiffness to its variable materials, stiffness variable materials. So we done some work with morphing scheme with the pure polymer, but we found pure polymer have some problem. So we reinforced with spandex. The reason we're using spandex is very flexible. So we also make some tube. The tube is also made by Shinmen polymer composite. The tube can change in stiffness. So we embed the tube in some soft polymer like elastomer. So this polymer can change in stiffness. And also we make some deployable wing. So you can see this one we covered with SMP, and we do internal test. This is initial work. Then we go to the spandex, reinforced Shinmen polymer composite. And with this one, you can improve the tear stress by the flexible, the elastic fiber, which is spandex. So we also embedded some tube, which is black color. You can see the tube is Shinmen polymer composite. So the tube can change the stiffness. So we embed this one in the rubber. So the rubber can change the stiffness 70 times. 59 times. You can see from the bottle. The modulus of this one can changing by the temperature. So that means if you cooling, it become too stiff and the loading, and if you heating, it become too flexible and moving. So this is another design. We make some deployable morphing wing using Shinmen polymer and the foam. So you can see the foam can change in shape. That means not only deploy for the wing, it also can change airfoil. You can see the airfoil can be changed. So other applications. The first one I want to point out is the smart manual. This one have a lot of applications. You see, normally to do the composite structures, like press vessels, complex structures, when you do filament bending, you have to have some manual. But the manual normally you can make either by the water soluble manual, which can soluble by water or different solution, or you can make some multi-piece metal manual, which is assemble and reassemble again, but it's very complex. So the people from USA, from the company called CRG, made this bottle, and right hand side is another air inlet. For this one, you can do the composite structures, then you can release after you do filament bending. And the bottom one is our student made someone do the filament bending, similar idea, and after that you can release, take off the manual easily. And we also done some simulation work by using FE modeling to see what is the deformation and the stress distributions. So this is another one for the air inlet. You see one side is circle, another side is rectangular. So normally it's not easy to take off after do filament bending. But with this one, SMP do filament bending. After that, the polymer become too smaller and soft, then easy to take off from the composite tube inlet. So we also done some simulations. So this is another one we call adaptive fracture external fixator based on SMP. When you have a bone broken, they will have original state with the swelling, and when deterioration coming, and the shape is reduced. So we using Shinmen polymer can fit this one. If you're using plastomer, normally the plastomer cannot change in shape. But with this one, you can change in shape. And also for the join, you can move to exercise, which is plaster cannot do that. We also demonstrated something during the last few years. The first bottle one is a flower. It's in the SPA conference 2008. You can see the flower can open by Shinmen polymer. Also, you can change the color. And I have to play again. So this one is called the SMP Braille paper. So for the visually handicapped people, they cannot see anything. They have to using finger to feel. So the idea for us is we made some shapement polymer sheet and firm, very thinner. Then we heating become too soft. Then we using some pen to make some dot. Then you reverse, you can feeling what that means. So after that, you can reuse in the heating again. So this is another design we using shapement polymer. You can see this is orange shape, which is micro cracking, and this one is recover shape, which is you can see very flat one. With this one, you can see this micro shape changing, which means this one can changing the contact angle. But the contact angle changing, we can control the wettability. The wettability can be changing and controlled by the micro cracking. You see this one, and here as well. So with that, I want to summarize. So we'll talk to you for the shapement polymer. In our university, we can do some synthesize, we can do some composite, we can do some deployable structures and morphing structures and other applications. So I think for the futures, shape can be changing in our life. So changing whatever, like car, like train, like transportation, like plane, or something you can see like the transform. So size can be small, from nano to macro to micro. And the reinforcement can be like a particle, fiber, firm. So shape changing can be used in anywhere. So, and I want to also introduce some other research activity in our research group. So this is another design using electroactive polymer. You can see the polymer can change in shape. So sorry, I have to play here. There are a lot of movie. So you can see this is this one also can move, and also we using this. This is a design for the student. The graph is made by EAP, so the electroactive polymer, they can grab something. And this one we call the energy harvesting devices. We make some devices in the water bath. When the water bath have some wave, this can generate some electricity. You can see, and this can flash the laser diode. You can see the laser diode can flash here. And also can do the phase expression in the futures. This was demonstrated this year in Las Vegas. And this one is another one. It's called flower. You can see this flower can deploy. And this one, you can see this crop. And this one as well. Can move. We also made some numerical muscle fiber, which is this one we embedded in some composite. You see this one can also changing shape. It's actuators, this one. And we also made some piezoceramic pump, which is here. This one is called the numerical muscle fiber, PAM. We have some collaboration with the University of Maryland. Sorry, there's no movie, but movie is there, so you can see. And also you can see this one. It can lift, and then also you can grab some things with this PAM. So we also have something work with control vibration by microfiber composite. Also some morphing structures, which like this one, it's called the Kurigami silicon cell structures. And also this one with negative Poisson ratio design for the flexible skin. So we're also working fiber optic sensors. With fiber optic sensors, we do something based on TDM, time domain multiplexing. With this one, time domain plus TDM, normally in principle you can get 1,000 sensors in one channel. So this is another design. So we're also working on acoustic emission sensors, which you have some impact and damage. You can locate the location of the impact by the acoustic emission sensors. We're also working with multifunction nano composite. The first one is bucket paper. Bucket paper is very similar nano papers, which made by nanotube. This very good conductivity, so we can do the de-icing made composite. You can see this ice here and the de-ice is here. We also can do the infrared sticks. We put some zero particle to improve the conductivity. Then they can improve the infrared sticks. Published paper here. In the futures, we also can do the lightning strike. This is a preliminary result with bucket paper and without bucket paper. You can see it's good for the protect the strike, lightning strike, and also can do structural health monitoring. Simply measure the resistance and electric resistance, then you can measure strain and stress. So this is another one we collaborate with the University of Birmingham using bucket paper to make some called flat lens. This is called a Fraser zone plate, FZP. We using the laser direct writing to make some lens. To make this one, because the bucket paper have higher shading efficiency in the terahertz frequency range. With this one, you can replace the conventional metal film with this lens. So we're also working with the electric spinning. We can do a lot of things by electric spinning. That is very useful. So with that, I'd like to acknowledge some of my colleagues from Harbin Institute of Technology, and also some collaborators who have contributions in my talk today, like David, Norman Bailey, and other person from the different university, from University of Maryland, from Bristol, from Cambridge, from Aston University, from University of Birmingham, from Davies, from the University of Auckland, New Zealand, and also Professor Sondi, Professor Huang from Singapore, Professor Peng from Zhejiang University, and Alan now is moved to Swinburne University of Technology, Australia, and also Dr. Jie from USQ as well. So this is our collaborators, Harbin and US, Australia, and Europe, and Asia area. So with that, I'd like to thank you very much for your attention, and I'll take your questions. So this is a deployable. Thanks. Thank you.
So thank you, Professor, for your nice presentation. And any questions to Professor Jinsong? Leng.
4D printing.
Yes.
I mean, so what is it about? I mean, 3D printing we know we can do, but 4D is how do you do?
Well, 4D printing means you have time dependent. That means when you finish your 3D printing product, the product can change in shape upon the stimulus.
Right.
So we also make some 3D printing devices. Recently, we made some micro stent. The stent made by shimmer polymer by 3D printing, but the stent can change in shape. If you apply some heating or magnetic field, the shape can change. So if shape changing from one time, say if you have a multi-shape, we also can call this one 5D or 6D printing. Okay. So 4D printing means you have time dependent. Yeah. So this is very important, but they need a special polymer. Normal composite only can do 3D, but 4D means the polymer can change shape again. Like a laser point, after that, this can change in shape. Yeah.
Okay, thank you.
Yeah, welcome.
Any other questions? Yes,
yeah, thank you. Nice talk. Just wondering, this material, shape-changing material, you said the antenna in the satellite, in the space actually is being using, or we still using the mechanical one?
Well, it's a good question. Actually, as far as I know, in US have launched 2 satellites, which 2006 and 2007, which deployed by the shipment polymer hinge for the solid state panel already. But other people are still working with this one as well. Yeah, because we need sort of a lot of problem for the deployable driving force, for the environment influence, and for the buckling as well. Yeah. But this one, I think in the future, there's a lot of applications, especially in space. Because in space, it's zero gravity, so especially for large structures, that is the benefit and advantage for shipment polymer. You can make very large structures and deploy easily. You don't need any motor or any something like mechanical devices. And also deploy is process is control. And unlike explosive bolt, this one don't have some dynamic impact. Yeah, so can make a very big one, I believe.
I just noticed that one of the application you mentioned, it's for arm or leg broken thing. So this material, you mentioned it needs heat or cooling, right? So with arm, at the beginning, the arm swelling, and then the size become less.
Yes.
So do the patient need to apply heat or cold, or it depends on the pressure inside the pressure?
Yes.
Thank you.
Actually, this is only preliminary demo. So in principle, we can just simply heating or using your arm to fix it. Then you're cooling. So this strip can be keeps it. But for the proper design, you need to think about it this one, how to do that. Yeah.
Thank you so much.
Yeah.
One of the question I had, Professor, is now you have done a lot of work at laboratory scale on smaller scale one.
Yeah.
But how, when you apply that for large scale, like in deployable big structures, what are the challenges we had to overcome, or are there any bigger challenges to look into that one?
I think the big challenge for the big structure is the buckling, and also for the fabrications. You know, to make a composite structures, because the SMP is different with other epoxy. Also, you know, for the we don't have a prepreg, maybe we need prepreg or other things. For smaller one, it's okay, you can hand lay up and something. But for the big one, you need to do the prepreg firstly, which is made by shim memory as well, polymer as well. Yeah.
Thank you. If there are no more questions, let's thank Professor Jinsong Leng for his nice presentation.
Yeah.
And thank you very much. You had made us to think a little bit beyond our normal thinking from 3D to 4D.
Yeah.
So similarly, we had to think outside this one, how the shape could be changed. And probably coming from civil engineering background, we'll be looking at potentially some future bridges that can change shape according to the driving speed and so on. So with that, let's give another round of applause to Professor Jinsong Leng. Thank you very much.
Okay. Thank you very much.